So it's my great pleasure to introduce you to Marta González, who works actually at the University Autònoma de Barcelona, which is where the ICMAB is located, and well, she's an expert on thermal properties of small molecules and many other things. So the floor is yours.
Thank you. So welcome everybody. Thanks for coming to the first session at 9. As Mariano was saying, I'm working at Universitat Autònoma de Barcelona, but also since last January, no, the previous one, we are also working together at ICN2. Part of our research is performed in ICN2, the Institut Català de Nanociència i Nanotecnologia. So yeah, we are I'm part-time in the two institutions. So the title of the talk is Thermal phase transitions in organic molecules, in particular ultra-stable glasses. But what I'm going to talk to you about is glasses. The thing is that this is my research topic. The thing is that I will use these glasses to introduce several concepts as phase transitions, different techniques for calorimetry, and in particular, we'll talk about vapor deposited glasses, which are what I'm doing my research on. I have prepared this talk more as a class than as a conference talk. So it can happen that people that are expert on or know more about these topics, they say, well, I know all these already, okay? But it's more like I thought about it more like a class than a expert conference, okay? So let's start. Let's start presenting what glasses are. In fact, glasses are, even if you don't know it, glasses are present in everywhere. They are everywhere. You can see here some examples. You will see more examples during the talk. Basically, a glass is an unstable system, okay? It's a disordered system, but so more like a frozen liquid, let's say, but with the properties of a solid. Okay, and we will see that how we can form them and which properties they have. But mainly now, we have to know that even we are using these glasses in many applications. You can see that in optical fibers, in pharmaceutical drugs, in windows. Okay, windows are basically silica glasses. We also have natural glasses like in amber or the lunar bed. In metallic glasses have a lot of applications. The problem mainly is that glasses are unstable systems. And the thing that they are unstable means that they are continuously evolving, okay? Imagine, for instance, that you have a pharmaceutical drug, which is made out of a glass. Why I do want to have a glass for a pharmaceutical drug? Because they are more, they can dissolve better in water, so you need a lower dose for this drug. But the thing is that if you have this glass and this glass is evolving, maybe if you leave it 1 year in the packet there, you store it for 1 year, their properties will change. And if the properties will change, maybe the dose that you were going to take is going to be smaller because it's more stable, and then if it's more stable, it's less soluble, okay? So we have a problem with that, but we will come back to this later. So how do we obtain normally a glass? Normally what we do to obtain a glass is to cool down a melt, okay? We start from the liquid. We start from the liquid, we cool it down, and here you have, according to free energy, diagrams. Here you have the melting temperature. So here we should have a first order transition that would take us from the liquid, which is the stable phase above melting temperature, to the crystal, which is the solid stable phase for any system, okay? We have here this first order transition, and then we form the crystal. This is if we are in equilibrium. But what happens if we are cooling this down and we cool it too fast? Okay, and if we cool it down very fast, this is what happens. This is the relaxation time. Everyone knows what the relaxation time is? Yeah? Relaxation time is the time that system takes when you move it from equilibrium with external stimuli, whatever, okay? You move it from equilibrium by compressing, by whatever, external stimuli, and then the time that the system takes to get back to equilibrium, that's the relaxation time. The thing is that a liquid has a relaxation time which is really, really small, okay? You disturb it, and very, very fast, you see, 10 to the minus 13 seconds. This doesn't have units, but this is seconds. So very fast, it turns back to equilibrium. But we are cooling it down, and the relaxation time increases. So the time that I need to move the system back to equilibrium is longer. If I go very, very, very fast, cooling down here, the relaxation time decreases. But what I am able to do is to avoid crystallization, to avoid the formation of a crystal. Why? Because to form a crystal, I need to form an interface. I need to get this, a certain crystal structure to form an interface to grow these crystals. And what I can do is that if I go fast enough here, I can avoid this, phase transition. When I avoid this phase transition, I'm getting a system which is called metastable, because the liquid is still stable, but it's not the most stable phase. So it's metastable. So we are here, but you see that the relaxation time is going higher and higher. We have longer and longer relaxation times. Okay, I'm coming to the glass transition finally. Here, what do we have? If we continue cooling very fast, the system arrives a moment that is not able to equilibrate anymore, okay? So it freezes. And this is the glass transition. Here, we have a system that has the microstructure, more or less, of a liquid, but the properties, the external hardness, etc., properties of a solid, okay? Why? Because here, the relaxation times are that big that in our time scale, human time scale, the system is not moving at all. Is not able to go back to equilibrium. So this is a glass. Basically, this is a glass. And the thing is that depending, as I said, depending on the cooling rate, this Q here are two cooling rates, this Q2 is another cooling rate, the glass we obtain is different. Why do you think the glass is different? Someone? This is a glass, come on. Which of these two cooling rates you think is slower? Q1 or Q2 is slower? Q2. Why? Exactly. Okay? Q2 is slower, so we are providing more time to our system while we are cooling down to stay in equilibrium. We move 1 degree down, and we'll have more time to let the system equilibrate before we continue cooling down. So the slower the cooling rate, the lower the state, the energy that the equilibrated state, let's say, we can reach. So the lower the enthalpy, the volume, or the entropy that I didn't say, but it's what we are representing here, okay? We are representing enthalpy, volume, or entropy as a function of temperature. So here this change was this step in temperature when we make the phase transition. Okay, so I think basically you know now what a glass is, how its stability, so enthalpy, volume, density, depends on the cooling rate, okay? So it looks simple, but let me tell you that the physics behind the glass transition are very complex, are really, really complex. To understand all these relaxation times, the distribution, etc., is very complex. And in fact, there are paradoxes. One is called the Kaufman paradox, for instance, that it's the fact that if this was entropy, these were entropy curves, if we could get an infinite slow cooling rate, we would reach a liquid. You see, this is the metastable liquid. We would reach a liquid that would have the entropy of a crystal, of an order system. And that's a paradox, that cannot be. So some people say that somewhere here there should be an hindered first order transition. And this is not solved yet, in fact. And more things that you should know about the complex of glass transition. In fact, one of the Nobel Prizes that was in this year, the one of Parisi, important part of the work of Parisi was dedicated to spin glasses. So it's a modelization, a particular type of glasses to study precisely the glass transition and the evolution of glasses. So it's a topic that it's really, I mean, there are really many open questions still. Okay, now we were going to talk about thermal properties. So what happens if I have this glass already and I want to analyze it? I want to check how stable it is. I want to check how is it going to behave with temperature. So for that, you see here the same curve that we had before. This is enthalpy. Before we had it on cooling, and here we were departing. This curve here is on heating. You see here, rising temperature. This curve here is on heating, okay? We started here in enthalpy. This is enthalpy, okay? We started here, and then we go to the extrapolation of the supercooled liquid line, okay? Till here, it's everything okay. But something happens here, and it's that at this point, this is called the fictive temperature, doesn't matter. At this point, if we are heating, again, fast enough, the problem is that we are not giving enough time to the system to equilibrate, because if we are heating faster than the relaxation time at this point, we are going to continue being a glass because the system doesn't have time to equilibrate. So we are going to pass this line out of equilibrium, and at some point we will reach a temperature enough, so a relaxation time small enough, so at this heating rate we are able to go back to equilibrium to the metastable liquid line, okay? So this is a typical enthalpy curve. What we can do to study our systems, we are not able to measure enthalpy directly, but we are able to measure using calorimetry. I will explain it later. Using calorimetry, we are able to reach the specific heat. You know, everyone knows what a specific heat is the heat that we need to provide the system to heat it up 1 Kelvin, okay? That's it. So from that, at least in thermal, in this kind of measurement. From that, if we derivate, well, in fact, it's the opposite. If we integrate the specific heat curves that we are able to measure with calorimetry, we recover these enthalpy curves, and from here we get a lot of information about stability, etc. Okay? So I'm showing you also these curves because at the end of the talk or in the middle, I'm going to show you a lot of calorimetry curves. So it's important that you identify what this means. This is the specific heat or the heat capacity, depending on if you are normalized by the mass of the glass. This is of the liquid, okay? We have here a transition, this transition from glass to liquid. And here we have this excess enthalpy that we had because we were heating too fast, okay? So in this way, you understand the curves. Does someone know why we have a jump in here in the specific heat curves when we do the when we have the glass transition from glass to liquid? No? Some of the experts of the ones that know more about the topic? No? This is because we are this is entropy. This jump here is due to entropy because here with this jump we are increasing the degrees of freedom of our system. Here it was frozen. So we had, in entropy, we had the disorder, but it was frozen. It couldn't move. The moment that we can move, we increase in entropy and we have this jump in a specific heat, okay? So these kind of curves provide a lot of information. And to get that, we use calorimetry. What is calorimetry? Again, I tell you, it's a class. Some of you already know, most probably. Calorimetry is the science or the techniques that allows us to determine the change in energy of a system through or via the heat exchange with our surrounding, okay? Measuring the heat exchange with the surrounding. So basically, very generally, we have like 2 ways of doing calorimetry. The idea is that this one, for instance, is the differential scanning calorimetry. What we do is to have a reference and a sample, the one that we want to measure. And what we do is at any moment control the temperature of the system. These are supposed to be sensors, you see, PP sensors. We control the temperature of the system, and what we do is to provide power so these 2 samples follow a certain temperature program. Let's say we want to heat it up at 10 Kelvin per minute, whatever. We heat it up at 10 Kelvin per minute, and the thing is that, and I have to provide certain power depending on the specific heat of the system, okay? The reference is supposed to do nothing during the heating. The thing is that if our sample is reacting, it can have an endothermic or an exothermic reaction, it will absorb or will release some heat. And if it does this, for instance, if it absorbs some heat, in order to keep the same temperature, this ramp, this thermal protocol, like the reference that was doing nothing, I will have to provide more power so we can heat it up. And the opposite, if the reaction is exothermic, it will provide power to the system, I mean energy to the system. So if I want to keep the same temperature, I will have to stop providing power, okay? So according to this amount of power I'm providing at any moment, at any time, and at any temperature, I get this kind of curves saying, no, this is power, in fact, but by temperature. So I get this kind of curves depending if the reaction was exothermic or endothermic, and I get these specific heat curves that I was interested. Another way of doing calorimetry, this one here, the DTA, this is differential thermal analysis, is that, again, I have a reference that does nothing. I have a sample that will have some kind of reaction. And what I do here is much more simple. I get less information, but it's much more simple. What I do is provide a certain amount of power, constant, all the time, and I check the temperature if it's going up or down according to the ramp I'm providing. And so if I have a delay or it advances too fast, so I get information about this kind of reactions, okay? But I get, this is less, I lose some information here. This is, as I said, no, this is a curve on an exothermic peak, an endothermic peak, depending if I'm giving more power or stopping giving power. Okay, yeah, please.
In a lot of these measurements in the literature, it seems that the baseline is kind of ramped. Is that a result of the feedback loop of the device, or is that something that's not calibrated well?
The thing, yeah, I mean, okay. The thing is that I didn't say that because okay. Yeah, it has a lot of things behind, okay? But the thing is that here you get the power you provide. Yeah. But it's not a direct measurement of CP. Okay. To get CP, you have to calibrate very well the system. Okay. That's one thing. The second thing is that in principle, this is flat, but this is fake. This is nonsense. In principle, you should, if you are accessing CP, even if it's not CP directly, but power, you should have a certain ramp. Yeah, okay. Because you have to provide heat to heat up the system. Yeah, exactly. It's a feedback. That depends a lot on the reference you're using. Okay. If the reference has a similar CP but with no transition, then you will have a flat thing because you're comparing the two. Okay. 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 But if you had just one, you should have a certain ramp. But it's all a matter of calibration. The baseline is a nightmare. Yeah. Okay. Okay. Yeah, thanks. It is. So what I'm saying, I mean, I'm explaining you is something that has been known, the glasses, the calorimetry, for more than 70 years already, okay? So this is quite old things. Still, I mean, it's important to know them because it's the basis, but this is old, okay? This is neither here, there's nothing new. What are we doing now regarding glasses, regarding calorimetry, and other techniques? So now we go to more recent stuff. I told you that glasses are unstable, so that means that this is back to our, this is enthalpy of volume, so back to our liquid cool. Then we have the glass transition here, we have our liquid cool. What happens, what I was telling you about the pharmaceutical drugs, what happens if I keep here at a certain temperature? At a certain temperature, the glass will gain stability. No? We'll have enough time to slowly, well, not enough, but it will start slowly to try to go to the stable phase, even if it's metastable, but to go to the stable phase. So the thing is that the system will evolve, and this is not bad, because the more stable the glass, the less will evolve. The more, no, that we can keep it there, and we know it's not going to change, especially if we go to very low temperatures. So we want stable classes, in fact, but from the beginning, we don't want them to evolve when we do our application. We want them already from the beginning stable. The problem is that this process here, to get something very stable, it's very, very, very long, really long. And it can take years to get a very stable class. So this is not practical. Another way of doing it to get a stable class is to cool it down very slowly. I mean, as some of you said, no, we can go down slower, so we go down closer, let's say, to the stable phase. But yeah, I mean, this has two risks. One is that you have to go really slow, which is not practical. And the other is that if we go very slow, we risk to crystallize, okay? And that's something that we don't want. So this is not practical, okay? We are using classes, but still we have some problems. But a few years ago, in fact, in 2007, so quite some time already, but not that long, in a group in the US, they discovered that by preparing glasses in thin film, as a form of thin film by physical vapor deposition, it was possible, depending on the deposition conditions, it was possible to change the original stability of the glass, okay? So the thing is that depending on the rate at which we were depositing the film, at which the molecules were arriving, this was with organic glasses, the molecules were arriving to the substrate. And depending on the substrate temperature, both things, it was possible to change the properties of the original glass. So you could get a vapor deposited glass that was not very stable, but you can also get a vapor deposited glass which is really stable. And when I say really stable, I mean that to get from here, like this one, from here to here, you need more than 1,000 years. So it's really stable from the beginning. We call them ultra-stable glasses, okay? And in fact, the conditions to get this very, very, very stable glass is very slow growth rate. I don't know how many of you are familiar with thin films and vapor deposition, but this is quite a slow rate, okay? 1 nanometer per second. And around this deposition temperature. TG was the glass transition temperature, you remember from before? So when you are relatively close to TG and go very slow, you can get a glass that is really, really stable. And these glasses are very interesting because it's the first time in history that we are able to have in a few hours, minutes, glasses with stabilities that otherwise we would need millions of years to obtain. So it opens a door to study a lot of properties of glasses that we couldn't access before. So we found out that these glasses, the ones that were very stable, had higher kinetic and thermodynamic stabilities. This is, we will go back to this, but this is basically that we need a higher temperature for the glass to get back to equilibrium. So it remains a glass more time, it doesn't change. Higher densities, they take less water. In principle, this for pharmaceutical applications is not that useful, but for things related to corrosion and things like that, it's important. The way they go back to the liquid is a bit weird. It's different because they are very dense. It's more similar to a crystal than to a glass, and have certain degree of orientation. I will go back to these properties because when I talk about the applications of these systems. And why is that? I mean, how can that be? That if I use a specific conditions for the preparation of the glass, for the film, to grow the film, we get a glass that it's that different from the conventional one that we were getting from the liquid. How is that? How can that be? This is a cartoon from an article that it's very, very interesting from Physics Today that tries to simulate, let's say, the vapor deposition process, okay? And this is done with the Tetris. The thing is that if our temperature is very low, for instance, in our deposition, if our temperature is very low, what will happen? It will happen that the molecules will arrive to the substrate, and when they get to the substrate, they don't have enough energy because all the energy is taken from the substrate, let's say. They lose a lot of energy and they cannot move. They lose a lot of mobility on the substrate. So the moment they get there, they get stuck. wherever, however they are, okay? They are just there. So you get a glass, a disordered system, which is like, not very dense, not very stable, because it didn't optimize its positions, let's say. However, if you go to a temperature high enough, then what happens is that the molecules have enough energy to explore what is called the energy landscape, to explore all the configurations, so they can adopt a better and more stable configuration, so a more stable glass. And the rate, what is the rate doing? Come on, what is the rate doing? I explained you why the temperature is important, why the rate is important. It's not difficult. Come on. Why is important the rate? No? We have to give time. I mean, the system needs energy to explore all the configurations, but this takes time. No, it doesn't happen immediately, okay? So if we deposit with a rate that is very fast, we are putting there all the molecules very fast, before the molecules we have on the substrate have time to explore the configurations, we are already burying them without possibility to move, okay? So we have to go slow enough to provide time for the molecules to explore this configuration. So if you go to very low rates and a certain temperature, let's say, it's optimus, and you get really, really very stable classes. So now, before I told you about the stability of glasses, we talk about calorimetry. The thing is that now we're working with thin film glasses. We're talking from, let's say, 20 to 100 to 200 nanometers, something like that, because these are thin films. Okay, you can do microns, but it's not feasible. But we're working with thin films, and we want to study the thermal properties. So where the glass transition was, all the things we were doing with calorimetry, the specific heat. But now we have thin films. And the glass transition, I didn't say that, but this jump that you saw, I mean, this peak, is very low energy peak. I mean, the energy involved is very small. So we want to do calorimetry on these films, but we have a problem. If we do conventional calorimetry, the ones that I was showing, we're not going to see anything with a nanometer size film and such a small amount of energy exchange. So we need a special technique. And that's why, I mean, not because of measuring this system, okay, but that's why we're using nanocalorimetry. Nanocalorimetry is a technique that was, was developed in the world in several places, more or less at the same time. One of these places was the group, the research group where I'm working. And it's a very special technique because it allows you to do calorimetry, but with thin films, okay, with a very small, or with samples that are really, really small. How does it work? In fact, the mechanism is really simple. The implementation and the electronics and everything is much more complicated. But the mechanism itself, the physics behind nanocalorimetry are really, really simple. In fact, it's the same DTA that I showed you before, exactly the same, but has several differences. For instance, how does it look, a nanocalorimetry? Let me show you. Here. This is a nanocalorimeter, okay? This is a microchip. You have the, I don't think I have the, no, I don't have the dimensions here, but this is more or less half centimeter by 3 millimeters, something like that, 5 by 3 millimeters, something like that, okay? And what do we have? We have a membrane, you see it here. This is a membrane, a silicon nitride membrane. And on top of that membrane, we deposit with a platinum circuit, okay? And this platinum circuit is acting both as a heater. You remember that we needed a heater to provide power and heat the sample. So it's working both as a heater and as a sensor. Why? The heater, because what we can do is to connect this, this is a 4-wire configuration. We connect this and provide a certain intensity that we know, okay? This intensity will heat up our platinum by Joule effect. So that's it, we have it, okay? But the good thing of platinum is that its resistance is quite linear. It depends quite linearly with temperature. Okay, so if you represent R, resistance, temperature, you get something that is quite straight. So if we know the resistance of the platinum during the treatment, we have access to the temperature. Okay, how can we get the resistance? Well, measuring the voltage. You know the intensity, you measure the voltage, you know the resistance, that's it. It's that easy, okay? So what we do is to deposit our samples here just on this platinum circuit, and what we do is to provide an intensity pulse here, very short one, and this is like the temperature profile that will follow the platinum without sample. If we have a sample here and it has a transition, then here we will have a small peak or whatever that we should have. It's like the DTA that I showed you before, okay? So this is basically the system, the nanocalorimeter. Why is that sensitive? Because all the heat, I mean, since this is a membrane and it's very thin, it's like something like 150 nanometers, all the heat that the sample takes or releases during the transition, all this heat will go into the platinum. I mean, we don't need extra heat to, let's say, to heat all the system. Okay, our system is not providing what we call thermal mass. It's not contributing our system because it's very thin. Okay, its mass is very small, so heat it up, it's nothing. We don't need almost heat to have the system equilibrated. Okay, I can go into the details if this is not clear a bit later. Okay, so yeah, one thing more. This is a pulse about whatever 35 milliamps, something like that. It depends what do you need. And since the system is that thin and its thermal mass is so small, you can achieve heating rates of around 10 to the 4, 10 to the 5 Kelvin per second, okay? The idea of going that fast is also that we don't provide, that you are experts, we don't provide time enough for the heat of the transition and the one that we are providing to spread into the rest of the system, to the membrane, to the frame. We don't give time enough. So we are working in quasi-adiabatic, it's written somewhere here, no, it's in the next slide. We are working here, we are working in quasi-adiabatic conditions. So all the heat that the sample is providing, we are registering it, we are getting it, okay? So it's really extremely sensitive technique. So we can get then afterwards the specific heat from the voltage, the heating rate, and the intensity. That I won't go here into detail. So we put our chips inside our deposition chamber, we prepare our samples, we measure them. This is an advantage because, for instance, they are in situ measurements. We don't need to take our sensors out, do the measurement, clean them, and then start again. In fact, if we are working with organic systems, if we heat it enough, it evaporates in the vacuum chamber, so we can use the same chip many times. It's very sensitive, as I told you, and we have high heating rates. This, I just finished here with the calorimetry, but these high heating rates have something else. Do you remember when I said, everything I said, I'm going to use it, the enthalpy curve, that one that was like passing the metastable line, and then we had this peak with the enthalpy, and then afterwards we were going back to the equilibrium. Okay, I told you that if we go very fast, no, you pass that equilibrium line. Now we are going at 35, 3 to the 10 to the 4 Kelvin per second. We're going extremely fast. So that's what happens. Our transition is shifted. If we go that fast, with the calorimeter, these nanocalorimeters, our transition is shifted to higher temperatures because we're going that fast that we don't give the sample time until we go to a very high temperature to do the transition, to go to equilibrium, okay? So this gives the advantage that we are able to explore a region that with conventional techniques, a temperature region, that with conventional techniques is not accessible. Okay, so this is so yeah, that you know the technique. This is the kind of measurements we are doing. This is a bit old, but still, this is the toluene. Okay, these are vapor deposited glasses at different temperatures, and you see here specific heat curves, as I told you. Okay, and you see that at a certain temperature range, let's say this 104 Kelvin is like the optimum. the peak of the transition is shifted to the right. This is performed always in the same conditions, same heating rate, everything. The only thing that changes is that we are preparing the sample at a different temperature. So you see that the peak is shifted to the right, so that means it's more kinetically stable. It needs more temperature it takes more time, let's say, to transform. And the area of the peak is also bigger, and that's related to the thermodynamic stability, to the area of how low we were there before going to the equilibrium. In fact, just to summarize, here you see the curve for the onset temperature. So at this region, more or less, in toluene is around 0.9. We have the most stable sample kinetically, and this is fictive temperature, and it's related to thermodynamic stability, so the lower, the more stable, okay? But you see that what I was telling you, we can tune the properties of our film, okay? The stability of our glass. Okay, this is regarding thermal stability, kinetic and thermodynamic. But these glasses have other properties, I told you. For instance, if we go to these very ultra-stable glasses, these special conditions, we get very dense glasses. These are our measurements from this group in the US that we're starting using, when discovering the ultra-stable glasses. And what you see is that we start from this glass here, okay, this is the as-deposited glass. These are two different glasses or three different glasses. We heat it up. These are measurements of density, of thickness, but this is done with ellipsometry. But from that we get density, okay? And you see that when we heat it up, then we go back to equilibrium, okay? This is the equilibrium line. And then when we cool it down again, the glass that we're obtaining, of course, is not that stable. And the difference in here in density is around a 6% can be. And it looks small, but a 5% in density in a glass is a lot. Okay, and this will have some implications in the applications that we can do with that. The density is bigger, therefore the hardness is also much bigger. In metallic glasses prepared in this way, you can get up to a 30% more hardness in your glass, which is very important. And also, as I told you, the resistance to corrosion and water update is also related to density in part. More properties of these glasses, and this is quite particular. These glasses, when you vapor deposited them, depending on the deposition conditions, that means temperature and rate, they can present different orientation and molecular packing. Okay, a glass, I told you, is a disordered system. If you prepare a glass from the liquid, the molecules or the atoms, depends if it's metallic or whatever, they are completely disordered. There's no correlation, okay? It's not order at all. However, if you prepare them by depositing, by vapor deposition, depending on the temperature range of deposition, here it's normalized to Tg, okay, but this is changing the temperature of the substrate. Depending on the temperature, we will have some order, but it's not an order, it's not exactly an order. It's more like a tendency to, for instance, the molecules get parallel to the substrate. So at a certain point, it's a certain degree of order, but it's still, you don't have correlations, okay? So we have the tendency to get our molecules more or less flat, only if the substrate temperature is low enough, because we are not providing time enough and temperature enough to equilibrate. Okay, if we are at equilibrium, this parameter Sz tells us the order. Let's say that if the molecules are more or less parallel to the or perpendicular to the substrate, a 0 means completely disorder, completely random. Okay, if we start going down in temperature, we see that the molecules tend to align. Okay, it's not that they are like this. Tend to align perpendicular to the substrate, okay? And if we go to lower temperatures, the molecules tend to remain flat. Still disordered, but flat. Related to this, although it's not exactly the same, but it's related, of course, is not only that the molecules tend to be flat, but also you start to have some correlation distances. If they are more or less flat, you see a packing, okay, that shows in, these are GWAX measurements, okay? You see that here, this is not completely random, because if the molecules tend to be flat, you also start to see a repeated distance here in the packing of the molecules, okay? And this gives you this, maximum here in the profile. So you see that here, depending, and you say, yeah, here, but this is not going down, as you were saying, no? This is not parallel. Yeah, but it depends on the shape of the molecule. If the molecule is like a rod, okay, it will tend to lay flat. If the molecule is more like a disc, it tends also to be flat. However, what we are measuring here is the orientation of the dipole, and the dipole is up, okay? So it looks like it's not the same, but both the upper curve and the lower curve, in all cases, is like the molecules tend to stay flat. And you say, yeah, why? I mean, two things. One, why is she telling us about this, okay? Why are we talking about this? And two, maybe you're curious that why is this happening? Maybe. Let's start with why this is happening. Apparently, these are modelizations. It's not 100% clear, but looks like it should be something like that. This is a simulation of an equilibrium liquid, okay? In an equilibrium liquid, bulk equilibrium liquid, you have, if it's in equilibrium, you have our molecules completely random oriented. Because in equilibrium, they should be disordered. In equilibrium of a glass, I mean, not in the, it's like a liquid. No, sorry, I'm saying it wrong. This is a liquid, so this is a metastable equilibrium. This is in equilibrium. So they are randomly oriented, it's a liquid. But if you go to the surface of this sample, you will see that you have a certain layer, let's say, that the molecules tend to stay slightly perpendicular, okay? And if you go to really the surface, on top, then the molecules tend, this is a problem of van der Waals force, etc., okay? The molecules tend to stay flat. So what's happening when we deposit our films? When we deposit our films, if we go to very low temperatures, we are in this region here. We are not providing the system time and energy enough to equilibrate, so we are depositing the whole system like this. Okay? If we go to a slightly higher temperature, what happens? It happens that the system has some time to equilibrate, but it only gets to here. We have to provide the system a lot of time and a lot of energy to be like this. Okay? And that's why here you have this region here corresponds to this, all this region here corresponds to this kind of behavior. This is the reason. But the thing is that this has some applications. And in fact, I'm going to show you finally some applications on thermal conductance, okay, or conductivity. We did some measurements in our group some time ago of measuring the thermal conductivity of our films, okay, of these glasses as a function of the deposition temperature. Okay, so we say that depending on the deposition temperature, the properties of the glasses are changing. We have different stability, we have different orientation, we have different density, okay? So what we did was to try to measure the conductivity of these films depending on the deposition conditions, okay? This is the deposition rate is always the same, but we only change the temperature. And these are special measurements because these are thermal conductivity. We are working with thin films, okay, you know that. These are measurements of thermal conductivity in plane, not out of plane, okay? This is thermal conductivity along the sample, okay? So this is where the orientation, in principle, you are measuring if they are flat or not. So we were interested in in-plane measurements. And this is what we got, okay? This is a TPD sample. This is an organic semiconductor that we use a lot and we study a lot. This is the deposition temperature. This is thermal conductivity in plane. These are different sets of measurements using different strategies. Doesn't matter now. And these are films that go from 150 to 340 nanometers. And what you can see is that the thermal conductivity as a function of the deposition temperature is changing, okay? And the idea now was to understand what was changing here. And the first thing to do the first idea, and you are more familiar with, you're familiar with this, is to correlate this change in thermal conductivity to density. No, if we knew we had more density, denser films at certain regions. So if they were denser, maybe the thermal conductivity was higher as well because the contact is better, etc. So here you have the same data than before. These blue points is an average, okay? This is the relative in-plane variation, so normalized to this value here, the 325, okay? But it still is the variation of the thermal conductivity. And you have here a curve of the variation, the change of density for this molecule as a function of substrate temperature. And as you can see very clearly, I don't need to explain, I think, it doesn't correlate at all. So even if in this region here, you remember around 0.8, 0.9, our films were much more denser, okay, the thermal conductivity was not affected. And that was weird. But there were other correlations to do. And here you can see the data, again, in blue, but now it's the opposite, okay? We turn it upside down. And here is order parameter. This is the same order parameter data that I showed you before, but only for the TPD molecule, okay? And you can see that they correlate perfectly. And this is not an artifact, okay? It's true. So the thermal conductivity in these molecules was strongly correlated to the orientation of our molecules. And this is not surprising because, there have been many studies that studied some time ago, that study thermal conductivity in polymers, for instance, and they could see that the thermal conductivity along the polymer chain was much higher than perpendicular. When you accumulate, let's say, your polymer in vertical. So there was a big difference, but there's a difference in here. Even if here we have our molecules oriented, all the bonding here is van der Waals. In a polymer, you have a covalent bonding along the chain. Here you don't have covalent. You have covalent inside the molecule, but it's very small, this molecule. You see it has only 2 rings here, okay? So still, even if it says, yeah, well, maybe it's intuitive, intuitively, I think it could fit. It's like, yeah, but that's strong. A 16% difference between these two. So what we did was to collaborate. You had yesterday Claudio at the first talk. We collaborated with the group of Claudio some time ago. That was 2018. So to see if they could simulate our system, our molecules, and with different orientation of the molecules, try to check how was the thermal conductivity. And they found out, let's see if it works. I'm sorry. Hey, wait. It's not here. But I tell you, I think it is still hidden, the slide, or maybe it will appear a bit later. I can explain you. What they did was to simulate molecules like pile up. If this was the molecule like this, they were simulating like a certain length of molecules piled up like this, and of molecules like one after the other, like in a row. Okay, these two systems, very simple, which are not exactly like this, because this still has some disorder, but just to compare. And they found out that the reason for this change in depending on the orientation in thermal conductivity was the fact that it was a problem, what they called thermal resistance. Okay, we have everywhere we have van der Waals bonding, okay, which is really bad. So the thing is that it was very, when we had the molecules like this, we had a lot of thermal resistance in the sense that each of these bondings between this molecule and this molecule and this molecule was providing a high thermal resistance, so the conductivity was not good in this direction. In this direction like this, you also had the same bondings, but for the same dimensions of the system, you had all the piece of the inside, let's say, the molecule, not even if they were just two rings, but this bone of the molecule was providing a spring, let's say, hard enough to allow the conduction of the heat with less thermal resistance, because for the same distance, let's say, you had less molecules. Okay, so it was something like that. I had the slide, but I don't know what happened. If it appears later, I can show you. Okay, so in principle, this was justified. It was published in this article you see here if you're interested. And we combined the thermal measurement, the conductivity measurement with the simulations. Okay, with this I finish. Is someone wondering how we did measure the in-plane conductivity? Maybe the ones that you are, more time in this topic, you know already. But normally, the conductivity measurements are done, well, there are many techniques, but in general, if you do it with 3 omega, you have for bulk samples, and in this case, if we had the film, we would have measured the out-of-plane conductivity, but we did measure the in-plane conductivity. How you do that? This has sense if you have thin films, of course. If you don't have thin films, you don't want it for anything. So for that, again, in the group, our group developed a technique, also in other places, it was not exclusively, but a technique that was called the 3 omega volt plane that allowed us to measure the conductivity of the in-plane, okay, in the film in the in-plane direction. You all, I probably know the 3 omega, all of you know, yeah? Here, everyone knows, so I don't need to explain it. Perfect, good. No, okay, so we have access to this 3 omega, but the configuration of the system is slightly different than the normal 3 omega, because what we do have here, you see the fabrication. This is again a membrane, okay? We deposit our film on top. This is the chip. We have a membrane, and on top of the this is the last slide. On top of the membrane, you see we have the filament that will heat up, and from the one that with intensity in omega, and it's again the one that it's providing the heat, but we'll also measure the voltage, the 3 omega voltage. We will measure it from this here, and from the resistance, you finally get the temperature. Okay, it's the same as the calorimetry, but with this strip here. So it's very, very similar. You see here the chip with the strip that will be the sensor and the heater, and yeah, you see the dimensions. This is for measuring thin films. You always need very, very small things. So with that, I think here it was coming the heat, whatever. Yeah, this is I won't explain. So wait a second, and I go to the. That was another application which was very nice, but it was too long. So, here. Thank you for your attention.
Thank you very much. Do we have questions?
Thanks very much for the talk. Very interesting stuff. I had 2 questions. So one is when the calculations were done about the film, was it also done where you had the perpendicular pi stacking?
Yeah.
So how come? Because that was not mentioned, so I assume that was not very interesting or maybe not important. But does that mean that the pi stacking does not facilitate any of the? No. Okay.
Exactly.
Okay.
Exactly. We thought it will. In fact, if you talk about, if you think about electrical conductivity, which is also important, there it does play. So in fact, these materials were thought, as a thermoelectric materials, because if you had a very, in this direction, in principle, with the pi stacking, you would have relatively good or better, let's say better electrical conductivity and worse thermal conductivity, but still the values are so small that.
Okay. And secondly, I'm quite curious about your opinion of the semantics between an ordered glass and a polymeric crystal.
Like
a polymeric crystal, like a section of a polymer that might be crystalline, because when you talked about the vapor deposition, that kind of sounds like a slow crystallizer or a fast crystallizer. I don't really know how the semantics there works, but I was just curious about your opinion of that.
No, these systems, what defines a glass, on one hand you have the disorder, okay, when you cannot have a glass if you don't have disorder, and the other thing that defines a glass is a glass transition. I mean, you can have disorder and don't have a glass transition, and then you don't have a glass. Okay, so, but normally all of them have a glass transition, okay? Most of them. So all these systems, even if they are slightly, I mean, here the cartoons are like, okay, they are all flat. It's not like that. I mean, it's tend to be flat. It's not really completely flat, okay? So these systems behave as a glass. They have a glass transition. Even when you do the X-ray, even if you have a certain tendency of packing and you see a maximum, you still have the whole ring, and here is like a maximum, but it's not a defined peak, so it's not really a crystal. It tends to be more ordered, and this provides some application. I mean, you can get from that, I mean, some applications. You can think about applications in OLEDs that I didn't show, but in OLEDs, in thermoconductivity maybe, for heat release. I mean, you can use that, but it's not ordered as a crystal, not at all. It's not a plastic crystal. It's slightly ordered.
More questions? While you think of a...
Thank you for the very nice talk, especially the introductory part. The didactic approach was very helpful for later. I had a question about the nucleation, because we mainly talked about the glass, but I guess that the crystallization is always a looming element that can happen. So how controllable is this? How reproducible is this? Do you get nucleation and sometimes everything is gone?
The thing is that in organic systems, that's what I'm working with, although in metallics there's a lot of work as well. In organic systems, you have molecules that are, let's say, better or worse glass formers. So if you have these are very, very reproducible, 100%. The thing is that for the molecules that tend more to crystallize because of barrier energies, etc., because of the kind of interaction with the molecules, depends a lot of things. With these molecules, in order to get a glass, probably you won't, I mean, you will only get the low temperature one. You know, the ones that are not really stabilized, because the region of higher temperature and more stable glasses, there you won't be able. I mean, because they will crystallize, because the energy barriers are smaller. But in those cases, you can only access the lower, I mean, the low temperature ones. Maybe not the ultra stable, but the lower ones. And in metallic glasses, for instance, is even worse. I mean, there, in fact, if you want a bulk metallic glass, you need to go to 10 to the 6 Kelvin per second in the cooling rate. I mean, otherwise it crystallizes. In thin films, they are doing a lot of work, but then again, the composition is very important. But then once you manage to get a composition that it's difficult to crystallize, then, I mean, it's 100% reproducible. You get the conditions, then it works. But not all, it doesn't work for all systems.
And another question is regarding the effect of the substrate. So you said that you have silicon nitride membranes. So I guess that it's going to affect very much the overall order of the
not really, yeah? No, not really. I mean, we have done, in fact, we are now doing absorption measurements, and we're using calcium fluoride, I don't know, many different types of substrates, and you are able to get that. The thing is that depending on the substrate, it can happen that with time, if you leave the sample there, with time it can crystallize faster maybe. But the original glass is possible to form. The conditions are enough, I mean, good enough, let's say, to form the glass. But again, that depends on the molecule. TPD, the one that we're using now, is a really very good former. So you can do whatever and you get a glass. There are other, naproxen, for instance, is a pharmaceutical drug. That one is a nightmare. I mean, it's very difficult. It's very sensitive to substrate, to things like that. So that depends a lot on the molecule. It's sensitive, but sometimes it's okay. I mean, it works anyway.
Okay. Thank you very much.
Thank you.
Thanks for the nice presentation. I have one doubt, and you were saying that you measure the in-plane thermal conductivity by using the 3 omega fold Klein method.
Yeah.
But in this case, you have like a silicon nitride membrane, and then you deposit the film over, I guess.
Mm-hmm. On the other side. Sorry, I didn't show it here, but you have the membrane, the filament, and you saw that it has the silicon like this. You deposit on this side, not on top of the filament. The filament is on the other side of the membrane.
Okay, but then to extract the thermal conductivity, you need to consider the thermal
the membrane.
Of the
yeah,
membrane
in
itself.
fact, you work in differential. You have to check.
You do differential.
You can do in differential,
okay.
And you can calibrate previously. In principle, the contribution of the substrate of the membrane should be always the same. In fact, we have another article where we follow the deposition of from the first stages of a deposition, just looking at the thermal conductivity. And then you can see when the film is continuous, when not, and what I was saying this, I don't remember. but yeah, I mean, and there you have the baseline that says the contribution of the membrane. Yeah, that was it.
Yeah, so I have a question. First of all, thank you for this insightful talk. So I don't know whether it's a relevant question or not, but you explained like with the like slowing down the deposition rate, you are getting some kind of more stabilized system. So can we relate the thermal deposition rate with the relaxation time for the phase transition, or is it a system property or not a morphological property, the relaxation time for the phase transition?
Oh, that's a very difficult question. I mean, relaxation time. Let's hear how to explain this. Even though I put here like the glass has that relaxation time, in fact, it's not that simple. The glass or even the liquid is formed by a certain distribution of relaxation times. You have like what is called a mosaic structure, where you have like different regions with different relaxation times. But one of the things that make glasses interesting and also difficult to understand is that microstructurally, okay, if you look at the microstructure, these regions with different relaxation time have no difference at all. If you look at microstructure or density or whatever, they are exactly the same, okay? You cannot distinguish them. But the relaxation time is different. But that you get already in a liquid, not only in a glass. Okay, is a matter of in certain of what is called a correlation length. Okay, but it's like the interaction between the molecules due to a certain configuration which is not distinguishable with our techniques. Okay, microstructurally we are not able to. We just see it amorphous. But the kind of correlation of interaction is slightly different in different regions, and that gives you a different mobility or relaxation time that you want. Okay, so that's what I'm saying. I mean, it's not that easy. Okay, the thing, and microstructurally you see the same. I don't know if it was more or less your question. Then when you have we deposit, you go down in this deposition rate. Okay, the rate at which we deposit. Of course, is correlated with the relaxation time at that temperature, definitely. But still, as I tell you, it's more complicated than what it looks, okay? But yeah. So for me, but the thing is that if you are high enough in temperature and slow enough in deposition rate, then you manage to equilibrate because you're going slower than the relaxation time at that temperature. So yeah.
So it's like a microstructure domain properties, like the different things have different relaxation time.
Yeah, but the microstructure is the same. No, that's why I tell you that it's the problem of correlations and statistics at the end. Not of microstructure. Microstructurally, you don't see any difference at all. But in a liquid, not only in a glass. In a liquid is known, the liquids that are formed by these regions that have different relaxation times, a certain distribution. But if you do X-ray, if you do whatever, you see exactly the same.
Okay, thank you so much.
Maybe we are a little bit over time, but Marta actually has to leave after the talk. She has some classes, so maybe while we have a couple of questions in Zoom, maybe Casper, would you like to start maybe connecting and so on, and then everything is done super fast? Okay, so then I read one of the questions in the Zoom, and then I'm sorry, but we need to move.
There's a question. Okay.
There were a couple, yeah, from someone called Christian Müller or something like that. Maybe you know him. So Christian is part of this consortium, and he's asking, thanks for the great presentation, Marta. Do you know of any work, possibly molecular dynamic simulations, that have explored how the geometry of a molecule, for instance, its flatness, affects its ability to pack in a glass?
Yeah, there's a work that's like maybe 8 years old or something like that from Juan de Pablo in the US, in Chicago, that he has a work that where they simulate just with balls, let's say, but a molecule with a certain shape, and then they try to simulate the deposition, and they get this curve for as a function of temperature, they get this curve for the orientation. So it has been reproduced by molecular dynamics. Not with real molecules, let's say, like more simple ones, but
I think he's referring to how the different flatness, for instance, could affect.
I think not.
The capability.
I think they did only like for a certain molecule with that like rod type, but they didn't try like with I as far as I remember to make it longer or this, because it was like so evident that it was working that I think they just thought that not to follow this line. But it's I mean, for one kind of molecule, it's done and it's reproducible, the experimental part.
I'm sorry, but we are a bit too late.
It's okay. Sorry, it was too long.
So thank you very much again.
Thank you.